Hello and welcome. In this video, we're going to take a look at limits at infinity. So a little different than what we were looking at previously with limits where x was approaching some sort of value. Now we're going to be taking a look at what happens mostly at the end of a function, at the end of a number line at both tails. You probably also notice that the scenery has changed a little bit, sort of a work in progress. So over the next few videos, you'll probably see a little bit of changes and a few other pieces of decor come up. It's pretty sparse in here right now, but you'll see that as a work in progress over the next few videos. Now let's dive in and take a look at limits at infinity. And of course, we'll start off with a brand new definition. Now we're still using function notation and limit notation as normal, where f is going to be some sort of function. But we're going to suppose that it's defined from some number a to infinity. And we'll write the limit of f of x as x approaches infinity equals L to mean that f of x can be made as close to the value L as you wish by choosing a sufficiently large positive value of x. And similarly, we can also define a limit of a function as x goes to negative infinity. And then f of x can be made as close to the value L as possible by choosing a sufficiently large negative value of x. And we'll see, of course, these limits may not always exist. Sometimes they do, sometimes they don't. So let's take a look at a couple examples. Okay, for a first example, a fairly straightforward function, the function 1 over x. And we should probably all know what the graph of this looks like. We've already maybe seen how this graph has a vertical asymptote when x equals 0. And if x is positive, it's going to be getting smaller and decreasing. If x is negative, then x is very small for large values of x. And as x approaches 0, we see it actually dives down to negative infinity as we approach 0 from the left. And so you can see that this function is defined, for instance, from 0 to infinity. Now that means that we can go and see what happens as x approaches infinity. Well, in this particular function, we can see that the farther we go outwards in the positive x direction, the smaller the value becomes. If we start by plugging in x equals 10, we get a tenth. And if we make 10 times larger than that, x equals 100, we're going to get f of x equals 1/100th. And these values keep getting smaller and smaller. We would say that it's approaching 0, even if it never does equal it. The value of f of x can be made as close to 0 as we wish by choosing a sufficiently large x. So we would say that the limit of f of x as x approaches infinity is equal to 0. We just have to remember that actually 0 is not in the range of this function. It never does equal 0. Now similarly, the domain of f also includes all numbers from negative infinity up to 0. And so it would make sense to then also look at the limit as x goes to negative infinity. And as x gets larger and larger in the negative direction, 1 divided by a very large negative number will be a very small negative number. And it continues to get smaller as we go further to the left. And so we would say this can be made as close to 0 as we wish by choosing a sufficiently large negative number. Now, not every function has this type of behavior. If we were to take something like a basic polynomial, for instance, a quadratic, let's use the example where a is positive. Now, the overall shape of this graph, we know it is a parabola, and it can be pretty much anywhere. It may cross the x-axis, it may not. I'll just draw a generic-looking parabola here. Now, because a is positive, this is going to be opening upwards. And it would make sense, since this is defined for all real numbers, negative infinity to positive infinity, that we could take a look at the limit of our function as x approaches infinity and see what happens on the far right. Now, thinking about traveling along the positive x direction as far as we can go, does it seem like the y values of this function are approaching some set number? You think by plugging values in for a larger x, it looks like it's just going to be increasing faster. The slope of this function keeps increasing, it keeps getting steeper. And as such, it never does approach a number. It can be made as large as we wish by choosing a large value of x. So the limit doesn't exist, but we would tend to write equals infinity, recognizing the limit doesn't exist, but it does imply that we can make f of x as large and positive as we wish. Now, traveling out to the left-hand side, if we wish to choose x be a very large negative number, because this is a parabola, as we go farther and farther into the negative x direction, it will also just continue to increase as much as we like. And so we would have to say this is also equal to positive infinity. Again, remembering that the limit doesn't exist, but we write positive infinity to indicate the behavior. If you take a look at this, these two examples of functions have very different behaviors at their ends, at their tail ends. One function is getting infinitely large without bound, and the other one is approaching a specific number, in this case 0. Now, the concept of f of x equals 1 over x, as we approach a larger and larger value of x, we call this behavior a horizontal asymptote. So, another definition, if the limit as we go to positive infinity or negative infinity, if it exists, then we have a horizontal asymptote, and we can give it an equation. So let's add that definition here to the list of things that we also can talk about for tail end behavior. Okay, to state the definition of a horizontal asymptote quite simply, if the limit of a function as x approaches infinity exists, or if the limit of f of x as x approaches negative infinity also exists, one or the other, then whatever their value is a horizontal asymptote. Now, to be clear, we can have one horizontal asymptote to the right, and we can have a different horizontal asymptote to the left. It only takes one or the other for us to have a horizontal asymptote, but because there are two limits here, it is possible to have two horizontal asymptotes. You may have to think about what kind of a function has two horizontal asymptotes. Luckily, we've actually seen one already. It's the inverse tangent function. The inverse tangent function has an asymptote at y equals negative pi over 2. As we're traveling further and further to the left, our function will approach that value and get as close to it as we wish. And as we travel to the right, it has another horizontal asymptote at y equals positive pi over 2. And the function can be made as close to positive pi over 2 as we like by choosing a sufficiently large positive value of x. Now, what about some other functions? Are there ways to test other common functions to see if they have horizontal asymptotes? Well, just like with some of the limit laws and being able to simplify and compute limits without graphing, we need to come up with a strategy for computing the values of infinite limits of other functions, particularly rational functions or radical functions. And it isn't too hard to do, but we need a couple very basic rules that we can work with first. Now let's think about some very common functions and what they do as x gets infinitely large. Okay, so first of all, we saw with a quadratic, it has tail end behaviors that get infinitely large. So that would apply to any kind of polynomial. If we take the limit of x, as x goes to infinity, that is going to become infinitely large. Now, of course, if we have the limit of x as x goes to negative infinity, then of course it becomes an infinitely large negative number. So we would say that limit equals negative infinity. None of these limits exist, but we can at least explain that it gets infinitely large. Now we can also take a look at powers of x so that we can make polynomials. And if we take a power of x as x gets infinitely large, this is also going to end up being infinity. So as long as n is perhaps greater than or equal to 1. And if we take a power of x and look at as x goes to negative infinity, then it is also going to become infinitely large, but it could either equal positive infinity if n is even, or negative infinity if n is odd. But in all of these cases, x's or powers of x to the n for n greater than or equal to 1, we see that the limit doesn't exist. It's always going to go to positive or negative infinity, which is why polynomials never have horizontal asymptotes. But then we can start getting into rational functions. What about if we were to take the idea that we had previously with 1 over x and we changed it to x to the power r for r greater than 0? Well, in this case, the bottom, the denominator, is going to get infinitely large, and 1 divided by an infinitely large number is going to get infinitely small, and we would say this equals 0. And the same thing, even if we choose negative values of x, 1 over an infinitely large negative number is still going to get infinitely small and approach 0. So this is definitely one of the most powerful tools to work with. It's going to be one of the many things that we can use to then evaluate limits of much more complicated rational functions. If we ever have 1 over a positive power of x, if x is going to get infinitely large, then the expression is going to get infinitely small. And now another common limit at infinity is using the exponential function. If you remember the exponential function, e to the power x has exponential growth. And if we have e to the negative x, we have exponential decay. In either case, there is a nice horizontal asymptote that we can use. So to add to this list, the limit as x approaches negative infinity of e to the x is equal to 0, and the limit as x approaches positive infinity of e to the x is also 0. And that's another useful tool that we can use when expressions involving exponentials show up. So let's use those tools and find out some common limits at infinity and see if other functions have horizontal asymptotes. Okay, here we can see that we have rational expression with a cubic in the numerator and a cubic in the denominator. Both the numerator and denominator are getting infinitely large as x goes to infinity, but what happens to the overall value? Now the trick here is to look for the highest power in the denominator and divide both the numerator and the denominator by the highest power of x, in this case x cubed. And that can be distributed across each of the terms in the numerator and denominator so that we can end up with smaller rational expressions and evaluate each individually. 4x cubed divided by 4x cubed is going to be 4, which is a constant. The x term, when we divide by x cubed, is going to give us a 1 over x squared. And then the final term will just be 5 times 1 over x cubed. In the denominator, the x cubes will cancel out of the first term, leaving with just a constant 2, and we end up with 7 times 1 over x cubed. And highlighting some of these individual pieces, we can look back at one of our very common infinite limits when we have 1 over x to the r with r greater than 0. As we take x goes to infinity, the expression goes to 0. So personally, I like to be able to cross these out and say that they get closer to 0 as x gets large. And we end up with 4 minus 3 times 0 plus 5 times 0 in the numerator, and we end up with 2 plus 7 times 0 in the denominator as x goes to infinity. And so the value can be made as close as we wish to 4 over 2, which is equal to 2. So the limit does exist, and this would imply that y equals 2 is a horizontal asymptote. Now, can we also take a look at what happens as x goes to negative infinity? Will any of this process be any different? Well, keeping in mind that anytime we have 1 over x to the r, as r is positive, as x goes to infinity, the expression equals 0, regardless of whether or not x is going to positive infinity or negative infinity. So y equals 2 is going to be a horizontal asymptote both at the right-hand tail and left-hand tail of this function. But let's look at a function that may have 2 horizontal asymptotes other than arctangent. Okay, in these 2 examples, we have the same expression involving a rational or fractional expression, but with roots. And they tend to behave very differently when we have negative values. In one example, we can assume x is positive because it is getting infinitely large in the positive direction. And in C, we can assume that x is negative because it's getting infinitely large in the negative direction. Now, we will need a quick identity here for how to take a factor outside of a root and distribute it into the root. if we take any expression, it should be equal to itself squared and then square rooted, right? Well, most of the time. If a is positive, the left-hand side is positive of this equation, and the right-hand side is positive, because a squared square rooted will always be positive. So this is a valid substitution if a is greater than or even equal to 0. But if a is negative, then the left-hand side of this equation is a negative expression, and the right-hand side is a positive expression, and they can't be equal to each other. So whenever a is a negative expression, to write that equivalently in a root would be using a negative sign in front of a squared square rooted. That's going to be our substitution that we can make if a is negative. That's going to allow us to use the same strategy as in example A by dividing by the highest power of x in the denominator, but using this substitution we can then distribute into the root. And let's see how that works. In this first example, x is going to be a positive number, which behaves a lot more as we would expect something to. We're going to take the highest power in the denominator as x cubed, and we're going to multiply top and bottom by 1 over x cubed. And that's pretty easy to distribute across the denominator. And distributing across the numerator is only going to be possible if we can combine two roots together. So we're going to have to make a substitution. 1 over x cubed is equal to the square root of 1 over x cubed all squared, which is 1 over x to the 6. And from there, we can use a nice property of roots. The square root of a times the square root of b is equal to the square root of a times b, and we can distribute. So that will allow us to combine two roots together and write this as 5 minus 2 times 1 over x to the 5, simply by distributing into the first root. And the denominator has already been distributed, and from here it's easy to use the property that 1 over x to the r for r positive as x goes to infinity is 0. And we'll cross off all of these 1 over x to the r's as going to 0, leaving us with the square root of 5 over 3. Now, what about taking the limit as x goes to negative infinity? It may or may not end up being the same result. We're going to be dividing by the highest power in the denominator, so we're going to be multiplying by 1 over x cubed. But we're going to have x be negative because we're letting x get infinitely large in the negative direction, and that means that 1 over x cubed is also going to be a negative expression. So if we want to bring that into the root, we can square it and square root it, but only if we also make the additional negative sign in front. So let's see how that changes our potential result here. The limit as x goes to negative infinity, and in the denominator it's easy to distribute because we don't have to make any substitutions. But in the numerator we have a root, and we can't just distribute into a root without being able to write 1 over x cubed as a root of something. So here's our substitution for negative expressions. It is equal to the negative square root of 1 over x cubed squared, which is the square root of 1 over x to the 6. And this negative sign is very key to how this is a different result than in the previous example. We can take that negative sign as basically a -1 coefficient and move it to the front of the numerator. And from then, we can distribute one root into the other. We can distribute the square root of 1 over x to the 6 into the square root of 5x to the 6 minus 2x. The rest of the steps are going to be exactly the same as before, and the only change is going to be this little negative sign. So we could already probably skip a step here because we know that the absolute value, that the magnitude of the result is exactly the same, you can see we're going to end up with square root 5 over 3 again, but we end up with a negative sign in front. So we have two horizontal asymptotes for this function, y equals root 5 over 3 and y equal negative root 5 over 3 are both horizontal asymptotes of the same function. Now, it may be worthwhile to see if you can then take this function, and I would recommend maybe use Maple or Desmos or some other function, even a graphing calculator, to try to be able to plot both of these. And or plot both of these and see what happens at the tail ends. So you might want to start with the rational function, and hopefully you can see that both tail ends approach the same value of 2. And in this other example, this function you're going to see approach two different values. They should get flatter and flatter the farther away you zoom out, because we're really just talking about what happens at the tail ends. Functions with horizontal asymptotes can do all kinds of interesting behavior somewhere in the middle of the graph for smaller values of x. We just happen to know what happens at the very far ends of the x-axis now. So I hope that sort of explains a little bit about horizontal asymptotes and gives you a better idea about how to evaluate limits as x goes to infinity. Keep in mind that if your expression involves e to the x's or e to the negative x's, you can do a similar process of dividing by the highest power of e to the x, perhaps, instead of the highest power of x in the denominator. And it's also got a lot of applications for later on topics when we're going to be looking at models of behavior, exponential models, for instance. You can kind of understand that certain behaviors approach a particular value asymptotically. Like, for instance, Newton's law of cooling. If you have a hot liquid and you pull it from a hot source to a cooler environment, you can watch the temperature decrease, but it will slow down exponentially and asymptotically approach the temperature of its environment. There are lots of cool applications as x or time goes to infinity, but we will try to look at those in class. Thanks for watching, and I'll see you in the next video.